Okay. All right. Today we'll talk about random number generation. Okay. So so far, we've been doing Monte Carlo estimation, just kind of showing you like what can be done when you with kind of these Monte Carlo estimates. You can estimate integrals, you can estimate all sorts of quantities. Okay. And all of these things, whenever we said, we want to get the expectation of this function h of x, where x comes from this random variable f, basically we turned it into the sample mean of h applied to a whole bunch of x values. But we've been able to draw random values from this distribution. Okay, so we've been able to draw values from this distribution. And so far, we've just been using R's ability to generate values from known distributions. So we've only done things where R has these distributions built in, like R normal or R beta or R, whatever distribution it is, that's what we've been doing, okay? And so what we're gonna do is we're gonna talk about how we're able to generate random values from distributions to begin with, okay? Traditionally, in a lot of Monte Carlo textbooks, they start here. They start with how to generate random values from distributions. I've chose to do the Monte Carlo integration first, just because I think that feels a little bit more like this is why we're doing Monte Carlo stuff in the beginning, and then we'll talk about generating random values. Just because, R is able to do a lot of this stuff, but we'll talk about how R is able to do this. Okay, and so pretty much all of these algorithms are going to depend on the ability to generate values from a random uniform distribution. So so we need to be able to generate values from a random uniform, and this is actually a challenging task. Okay, like how do we get random uniform values? Okay, and it used to be, so this was maybe, I guess, close to 70 years ago or something. You would go, if you were a researcher and you wanted to, and you needed random numbers, okay, you would have to purchase some tables, okay, like this, where they would just publish a bunch of numbers here, okay. And so so this came, so you'd have to, so there would be a company like Rand that had access to this machinery, basically large computers that were able to generate random numbers. And then you'd buy a book, okay, it's like 1 million random digits, and then this is what the book would look like, okay. And so if you needed random numbers, sorry, there's a machine going off in the background. Okay, you would just consult all these things for like random digits, okay? And you would just look at your table, and you would have 600 pages of these numbers here, and that would be your book with 1 million random digits in it, okay? I mean, you can still buy this book just for fun, but I don't think you would need to, right? Because being able to generate random numbers on your own computer, that was not, well, people didn't have their own computer. Okay, but today we're able to kind of generate these random numbers. I was debating whether or not I should put in this this slide, but I did anyway. And whenever we talk about random numbers, I always just kind of like to pause and think, like, is anything truly random? Because oftentimes we think about like coin flips and rolling a die as these random events, but then like if you knew exactly like how much force was being applied to the coin, and like the properties of like the material properties, and how it's going to bounce, and wind resistance and all of that, like could you predict how the coin's going to land? Or same thing with the die, right? Can you predict, like if you knew exactly all the forces involved, like can we predict that? And then also just like, so, you know, is any of that random, or is that all kind of just subject to the laws of nature? And I think it's just subject to the laws of nature. And then if you think about like what's happening inside of your brains with what you're thinking and all of that, it's really just like electrical impulses firing, and your neurons are just reacting to stimuli. And so, you know, is that also, you know, is there any kind of freedom there, or is it all kind of predetermined? And, you know, and then you start going down this rabbit hole of thought on, you know, is there free will and stuff like that. You know, I think if you study quantum mechanics, they talk about there being true randomness at the quantum level. And you know, Einstein famously argued that it's not truly random, that there's that they just don't understand. They're not able to observe what's happening on the inside, and they don't fully understand what's happening. But if you talk to people who study quantum mechanics, they're gonna, I think they would say Einstein's wrong, but then, you know, anyway, what's all this randomness stuff? But anyway, that's beside the point. That just, you can go on Wikipedia and look up free will and randomness and spend hours reading up on it. It's kind of fun, food for thought. But anyway, you know, back to our class, we are we'll talk about pseudo random number generators, which is basically everything. Whenever you call for a random number in your computer, it's a pseudo random number generator. And if you think, and so pseudo random number generators are actually not random at all. They are deterministic. Okay, they like your computer has no choice but to generate this sequence of numbers. Okay, it's not random at all. But pseudo-random number generators are designed in such a way that the numbers that they produce behave like random numbers. They look like random numbers. They behave like random numbers. And for all intents and purposes, we can kind of use them like random numbers. But they are deterministic, which means that whenever, if you provide the same seed to the pseudo random number generator, it's going to produce the same sequence of values. Okay, and that's how we're able to kind of reproduce results on our computer, and that's actually an important thing. Okay, for reproducibility, we want pseudo random number generators. Okay, and this was a very important topic area of research for several decades. You know, kind of in this era where they were dealing with, you know, tables of random numbers. They wanted to be able to generate these quickly, and so that was an area of research now. But you know, I would say not so for the last 20 years because, well, you know, we got the Mersenne Twister, and so now this is probably considered a quote unquote solved problems. So they don't do this. Okay. And so I'm going to talk about one kind of algorithm that was used as a pseudo random number generator. And this is the linear congruential generator. Okay, it's kind of one of the oldest and one of the most well-known methods for generating pseudo random numbers. And it basically generates the next random number based on the current one. Okay, and you take your current value, or if it's the very first value, you call this your starting seed. Okay, you take your current value xn, and then the next value you generate is you multiply your current value xn times a, you add some constant c, and then you do you know, mod whatever it is, right? Modular. You basically divide by m, but then you only keep the remainder. So you do modulo m, and then whatever that comes out to be is going to be x, the next value you use, okay? And you just kind of pick arbitrary values a, c, and m, but your choice of values will have significant effect on what numbers it generates, okay? So for example, if I start off with seed 1, a is 2, c is 0, and m is 9, you're going to get a very, very, very terrible pseudo random number generator, okay? So you would start off, you'd plug in 2, a is 2, x is 1, okay, plus 0, mod m, okay? So that becomes 2 mod 9, or 2 mod 9, okay, which is just 2. Then you plug in the next number, and 2 times 2 becomes 4, okay? Or 2 times 2 plus 0 becomes 4. 4 mod 9 is 4. And then you plug in 4. 2 times 4 is mod plus 0 is 8. 8 mod 9 is 8. And then you plug in the next number, and you get 8 times 2 is 16. 16 mod 9 is 7. You multiply that by 2. 17 times 2 is 14. 14 mod 9. So, you know, if you do 14 divided by 9, you get 1 remainder 5. So the mod part is 5. Okay. And then you do 5 times 2 and you get 10. 10 mod 9 is 1. Okay. And then you're back at the beginning, right? 1 times 2 is 2. 2 mod 9 is 2. And so you're going to end up getting, you're just going to get this cycle of values, 2, 4, 8, 7, 5, 1. Okay. So every linear congruential generator has a cycle, okay? It's gonna cycle around. But if you select the correct, not correct, but if you select a good combination of A, C, and M, you can kind of create a cycle length, a period length that takes a very, very long time before it starts repeating itself. Okay, is that all right? What's happening here? Okay, and so you know this is like a very these are very bad settings to use for a pseudo random number generator. Okay, but you know, but this is how we would program it. Okay, it's just a times x plus c mod m, right? And so here we're going to create a function. We're going to start off. How many values do you want? What's your seed in a, c, and m? Okay. And then I create a vector called output, which is what it's going to return. I plug in the seed, and then we're going to just do a times x plus c mod m. Okay, and that's going to be our next value of x, and we're going to just kind of store it into output underscore I, or output sub I. Okay, and so here we can see if I do this, I get this sequence 2, 4, 8, 7, 5, 1. 2, 4, 8, 7, 5, 1. It's just going to continue repeating, which is exactly what I get here. Okay. So that's the linear congruential generator, and so an older standard of the C language. Okay, so you know, they don't teach straight C anymore, but generally, if you've taken like Pic 10 or CS31 or something, you would have learned C++, which is basically a derivative of the C language. And but anyway, so C was developed in Bell Labs. So was the predecessor to R, Bell Labs. So everybody today, like the high-end research in terms of like algorithms and machine learning and all of that stuff, that's like happening at Google and Facebook and Apple and Microsoft and stuff like that, right? Netflix and Amazon. So those are kind of like the labs that are developing like cutting edge research, you know, along with the universities. But then but back in the day it was Bell Labs. Bell Labs used to be, you know, the parent company of basically all of the phone networks, and they were doing the research. So they developed all kinds of cool stuff. C, you know, they developed the computer language C, which is very powerful. And they also developed the computer language S, which eventually kind of the open source version R is based off of S. But anyway, so So anyway, if you pick these numbers, A being whatever this number is, okay, and C is 1, 2, 3, 4, 5, and M is 2 raised to the 31st power, you're going to get a this linear congruential number generator will generate a whole bunch of values with a period length of basically 2 to the 31st power. Okay, so it's not going to repeat itself for 2 to the 31 with a length of 2 to the 31. Okay, so you do this, and so here I just generated kind of 10,000 values, all right, and I using kind of the same code, this same code that generated this terrible sequence. If I just change what my AC and M are, okay, if I change AC and M to this, then I can generate a whole bunch of values, okay. Now, the values come out like this size. So to kind of scale it, I'm going to take X and I'm going to divide by 2 to the 31st power, okay? And if I do that, then I'm going to get this, okay? I'm going to get histogram. Looks pretty uniform, okay? Fairly uniform, not perfectly so, but fairly uniform. And I can plot the empirical CDF function, okay? And if you recall the empirical CDF, here in black is basically the empirical CDF of the values that I've drawn. And we want it to align closely to the red line, which is the theoretic CDF of the uniform distribution, okay, going from 0 to 1 like this. And we can see we get a fairly close match here, okay. So that's a linear congruential generator. It's a very simple algorithm, but it worked for it was what was used in computer languages for several decades because it performed well enough, okay. But you know, there's some issues with it, and particularly if you need more than 2 to the 31 random values, then this is not going to cut it. Okay, and so there's another. So this algorithm, the Mersenne Twister, I don't know if you guys have heard of it. The Mersenne Twister is probably the most popular choice for generating random numbers. Okay, it is it's the default choice in R, Python, MATLAB. I think a lot of versions of C++ and a whole bunch of other languages kind of rely on the Mersenne Twister. And it was developed in around 97. And basically after this algorithm was developed, you know, it was put through a whole bunch of kind of statistical tests to see like how well does it perform, and it passed a lot of them. Okay, it passed a lot of them. Right? Maybe not every single one, but it passed a lot of them, and it basically has won. Okay, and so now the this problem of generating pseudo-random numbers is kind of considered to be a solved problem, and we don't spend a whole lot of time discussing the merits and demerits of different random number generators. Okay, the algorithm itself though is very complicated. You can try going on Wikipedia and try reading about how the Mersenne Twister works, but I don't really understand. Okay, it involves like bit shifting. Okay, so it's like, you know, you get a number represented in the computer, and then you just basically shift all the bits, which is basically either like, it's kind of like multiplying by 2, but then again, it's also a little bit different because, you know, you're shifting the bits in the kind of different parts of the, you know, how the number is designated. Okay, so anyway, the Mersenne Twister is very good. There are some issues. Okay, one is that it is not cryptographically secure. So some like banks and stuff need to generate like random authorization keys. So like when you log into your bank, it needs to generate like a random kind of key for your computer to authenticate with that. And so the Mersenne Twister is not going to be good for that because it's because if somebody observes enough observations from the Mersenne Twister, they can kind of reverse engineer or figure out what seed was used. And if they can figure out what seed was used, then they can figure out the next values that it's going to generate. So it's not good for something like that. But if you're not doing something like, if you're not trying to do an encryption stuff, Mersenne Twister is fast, it's reliable, and it's going to be more than adequate for pretty much all of our needs. So this is the algorithm that we use. It's got a huge period length, so it's going to go 2 to whatever this power is before it repeats. Okay, so it's going to it can generate like basically this many numbers before it repeats again. All right, and this is a Mersenne prime, and that's where it gets its name. Okay, so anyway, we're gonna assume now that we're able to always generate values from the random uniform distribution. Okay, so we're always going to assume that we can generate values from the random uniform distribution, and that's going to kind of form the basis for all of our future random variable generations. Okay, and that's and we're okay with that because we've got the Mersenne Twister, right? I showed you a little bit of the linear congruential generator, the LCG, which was, again, what was used historically, but not anymore, not for the last 20 years. Okay, so uniform distribution is, the PDF is 1 from 0 to 1, and it's 0 everywhere else. Okay, so it goes 0, and then from 0 to 1, it's 1, and then beyond 1, it's back down to 0. Okay, and it's very easy to get random uniform numbers, and you can do RUnif. Technically in R, like if you you go to R and you type in $RNG, are you guys able to see this? I don't know how to make my help bigger. Okay, so there's technically different random number generators that can be used. The default is Mersenne Twister, though, which is what you've got. But then if you wanted to read up, these are different algorithms that that can be used. All right, but we use RUnif here. Okay, so the first method for generating random numbers or values from a random distribution is going to be the inverse CDF method. Okay, inverse CDF, or also called inverse transform method, basically uses the inverse of the CDF function, right? So you've got your cumulative distribution function, and we're going to take inverses of it, the inverse of that, to generate values from a probability distribution. Okay, so the definition of the CDF is this. Okay, this is how we define the CDF. F of x, big F of x, is a probability of x being less than, so, random variable x being less than, whatever value x is, and that's defined as the integral from basically -infinity to x of your PDF, f of t dt. Okay, and so what the CDF does is it takes the support of x, okay, whatever the support of x is, and it's going to map it to the interval 0 to 1 because it's equal to the probability, right? And probabilities always go from 0 to 1, and the PDF integrates from 0 to 1, and so whatever it was, it's going to map the support of x to the interval 0 to 1. Okay. And kind of this, it relies on this one kind of fundamental relationship that exists between that exists for the cumulative distribution function, right? And so there is a kind of this relationship. do you guys talk about this in like 100B, the probability integral transform? Does that sound familiar at all? No. Okay. Basically, well, has anyone told you that the CDF of any random variable is uniformly distributed? Like if you take, okay, so this is basically it, right? All right, so basically if you have some random variable x, whatever x is, it's a beta distribution, it's a normal distribution, it's a gamma distribution, any distribution you can think of, okay? If x has this CDF, if it has this cumulative distribution function, then when you take the CDF of random variable x, okay, and you just call that u, all right? So if you take the CDF of random variable x, this variable u is going to be a standard uniform distribution. It's going to be uniformly distributed on 0, 1. Okay, so the so basically what happens is that the CDF function, CDF f of x transforms is transforming x into a uniform distribution, okay? And so the inverse of that will transform from the uniform back to x. Let me just kind of demonstrate this thing, right? Because I don't know if you guys ever thought about this, but it also kind of makes sense. So if I generate like z is R norm, let's just do 100,000 values, and I do histogram of z. Okay, that looks like the normal distribution, right? Okay, but then if I take, if I call y, and I say this is just the CDF, okay, and I say what's the CDF of z, and I call that y, what's the histogram of y going to look like? It's going to look like the uniform distribution. Okay, and it could be anything else, right? So if I say z is R gamma, and we're going to ask for 100,000 of these things, and let's do shape equals 3 and rate equals 1/2. Okay. Histogram of z is this. All right, so that's the kind of the density of z. Okay, and then if I say y is going to be the CDF p gamma of z, okay, and I have to kind of provide it the shape, the same shape. All right, so p gamma is the CDF, and I ask what's the histogram of y, it becomes uniformly distributed. Okay, and you can kind of try this with any kind of combination. Just generate random values from something, okay, and it's going to have that distribution, and then when you apply the CDF to it, the result becomes uniformly distributed. And if you think about it, I think it makes sense because basically when we do p norm of z, we're basically asking what's the probability that some value is going to be less than 0 or something, and that's going to be 50% of the time, and that's going to kind of correspond to y being equal to 0.5 as well. So anyway, this is what you get, all right? And so we're going to basically take advantage of that, all right? And we're going to say, well, this function f takes x and it maps it onto the uniform. So then that means the inverse must do the opposite. Okay, if we start with the uniform 0, 1 and we take the inverse of it, then that must map it back to x. Okay, and that's basically what we're doing. Okay, so we've got x, has this CDF function. Okay, CDF, and so the inverse transform is basically the inverse of u is basically the the inverse. So this is what the how we define the CDF. CDF is the probability that x is less than equal to x. And so the inverse of that is basically what value of t do we use so that f of t is basically equal to u, okay? But we have to kind of throw in this min business here, just in case there's like a spot inside the function. So if there's a spot that's flat in the CDF, when you invert that, because if you think of like a graph, when you take the inverse of a function, it kind of flips it around the line y equals x, right? So if it goes from here, it becomes like this, right? So this is when you take the inverse of a function. If the function goes like this, and you take the inverse, and then it goes this way, right? And so so if when you take the inverse of a function or any function, you can't have a vertical line, and so that's why we've got this min business. Okay, so this is going to be this part, min t, is the smallest value of t that satisfies the criteria that f of t is greater than or equal to u. Okay, generally it's going to be basically the value of t that satisfies f of t equal to u, but in some cases it might be the smallest value that satisfies this. Okay, and so if u is uniform this, then the inverse of u will have this distribution f of x. And so to kind of just prove that this works, we'll look at the distribution of the result of putting a random uniform number into this thing, right? So we're going to put a random uniform value into the inverse function. Okay, so we're going to say, all right, what's the distribution of, what's the probability that f inverse of u is less than x? Okay, so what's the probability that f inverse of, some uniform value u ends up less than x? Okay, so so basically this is the definition of f inverse of u, and if you apply f to f inverse, okay, what's f of f inverse? F of inverse is just whatever's inside, right? So f of f inverse becomes u. Okay, and on the right hand side, so over here I've got f inverse of u less than or equal to x. I'm going to apply f to both sides of this thing. Okay, so I'm going to get f of f inverse, and over here I got big F of x. Okay, f of f inverse of u becomes u, and big F of x is big F of x. And then we just say, well, what's the probability that u is less than big F of x? That's just going to become big F of x, because the probability that u is less than or equal to p is just p. Okay, when u is uniform. So any value p here, probability that a uniform value is less than some number is just that number. And so the probability that u is less than big F of x is just going to be f of x, and therefore this function, the distribution of this random variable is exactly equal to f of x, which is what we want. Okay. All right, and so this is how the inverse CDF method will work. Okay, I've got a few examples, and we'll see if we get through all of them. So first, and this is the hardest part, is you have to derive the inverse function. Okay, so if you've got the CDF, you have to figure out what the inverse CDF is. Okay, and sometimes this is a difficult thing to do. Sometimes you have a function, and finding the inverse of the function is hard. Okay. But if you can do it, then you can do inverse CDF method. All right, so once you figure this out, all you do is you generate random uniform values, and then you plug those random uniform values into your inverse function. All right, and so this is going to work as long as the inverse of the CDF can be found. And it will work for both continuous and discrete. Today's examples are just continuous, and then on Wednesday we'll look at discrete ones. We'll see if we get through all of our continuous examples today. I think we will. Maybe we not. I don't know. Okay, so so let's say you just want to generate values, uniform values on the interval AB. Okay, so we want to go from uniform values from 0 to 1. We're able to generate standard uniform values on the interval 0 to 1, but let's say we want to generate values from on a different interval from A to B. Okay. And so the PDF of that uniform variable is going to be 1 over b minus a for any elements inside a and b, and it's going to be 0 everywhere else. Okay, and therefore the CDF, okay, is the integral from a to letter x. Big F of x is going from a to x of the PDF 1 over b minus a dt. Okay, and so when you do that, you're going to get x over b minus a over b minus a, and that becomes x minus a over b minus a for x between a and b. Oh, I've been forgetting. I forgot. I got to give you quiz answers, right? How are you guys doing? Is this all okay so far? Okay, I'll go ahead and give you your first 2 quiz answers, which will be E and C. E as in elephant, C as in cat. E as in elephant, C as in cat. So those are your first 2 quiz answers. E and C. All right. What did I say? Okay. All right. Okay. So now we want to find the inverse of this, right? So this is the CDF. The CDF of the uniform on A to B is x minus a divided by b minus a. And the uniform distribution, the inverse of that CDF, okay, we're going to set f of x equal to u, and then we're going to solve for x, right? So I got big F of x is x minus a over b minus a. We set that equal to u, all right? And then I solve for x, so I get x minus a is equal to b minus a times u, and then I add a to both sides, and I get x is equal to b minus a times u plus a, right? So this is the inverse function. I didn't have to worry about this, min t, min t of, whatever f of t that satisfies greater than u or something. Okay, I can just find the inverse, the usual way of finding the inverse function. Okay, so this is what we have. And so let's say we want to generate random uniform values on the interval 10 to 20. Okay, so the inverse CDF, okay, is 20 minus 10, right? It's b minus a times u plus a. So 20 minus 10 times u plus a, 10. So that becomes 10u plus 10. And so if I generate uniform equal to 0, then I'm going to get, if my random uniform is 0, I get 10. If my random uniform is 1, okay, then I get 20. X becomes 20. So that the range 0, 1 maps to kind of the range 10 to 20. If u ends up like 0.5, it's going to become 15. If u ends up 0.22, then we're going to get 12.2. And I think it can be clear that, u goes between 0 to 1, and that's going to map to the uniform on 10 to 20. Okay, here we've got the exponential distribution. All right, so the PDF of a random exponential variable with rate parameter lambda is this is the PDF, right? Lambda e to the negative lambda times x. Okay, and the CDF of this, all right, is going to be 0 from 0 to x of lambda e to the negative lambda t dt. Okay, and if you solve for that, you're going to get 1 minus e to the negative lambda x. Right, so this is the CDF of the exponential distribution. Okay, and the support of the exponential distribution is basically all positive values of x, right? So everything, or all non-negative values of x. Okay, and so here's, we got to find the inverse. Okay, the inverse of f, all right, we set big F of x equal to u, and we're going to solve for x. So big F of x is 1 minus lambda, 1 minus e to the negative lambda x equal to u. I'm going to bring the 1 to, well, basically, yeah, I can subtract 1 from both sides, okay? And then multiply by a negative 1. So I'm going to get e to the negative lambda x is equal to 1 minus u. Then I take the log of both sides, and I get negative lambda x equals log of 1 minus u, and x is equal to negative 1 over lambda log 1 minus u. Okay, so this is how we can go from the uniform to x, right? Now, one thing to note is that the variable 1 minus u has the exact same distribution as u, right? Like if the variable u is uniform on 0 to 1, then the variable 1 minus u is also uniform on 0 to 1, okay? So just to kind of simplify things, I think you'll often see the inverse CDF reported this way as negative 1 over lambda log of just u, okay? The inverse CDF method for the exponential distribution is this. You can also use this. These will have the same distribution, okay? So if you have a random uniform u, you can plug in 1 minus u, or you can just plug in u, okay? And you'll get a random exponential, okay? These will generate different values, but overall, if you're using random uniform values, you're going to get the same distribution here. All right, so so if I use this, so if I do exponential 1, then and I plug in these values, the random uniform will produce the following value. So if your u is equal to 0, then it's going to generate infinity, okay? Now the probability of getting u exactly to 0 is 0, so the probability of generating an exponential of infinity of infinity is also 0. But and then also if u equals 1, then x is going to equal 0. And then you kind of have all of these values in between. So if u is equal to 0.1, you're going to get something like 2.3. At 0.5, you get something close to 0.7. And at 0.9, you get something around 0.1. Okay, so on and so forth. So that's going to be kind of just how it maps here. And so here, I tried generating a whole bunch of these values, right? So I generated uniform values using random uniform, okay? And then I'm going to apply the inverse CDF function. So the inverse CDF of the exponential is negative log u, okay? So that's going to give my x. And then I created a histogram of my values that were generated, okay? And I compare that to the exponential density, right? And so we can see that we get pretty good match between our histogram and the theoretic density. Okay, so that's pretty good match. So that's I mean, that's far from a proof that this is correct, but that's a good sign. Okay, here I can plot the empirical CDF versus the theoretic CDF. Okay, so the theoretic CDF you graph by doing p exponential, okay, and that's going to be the theoretic CDF in red, okay, and then the empirical CDF, which we've talked about using the values that we observed, is in black, and we see that the black and the red line match almost perfectly here, okay, and then here's a statistical test. I don't think you guys have learned this, so I'm just going to mention it here. This is the Kolmogorov-Smirnov test. These are basically Russian mathematicians or statisticians that developed this test. And it can be used to see if a sample of values that you have came from a certain distribution. That's what we're doing here. That's the one sample KS test. But then you can also have the two sample KS test, and basically you give it two samples, and it's a test to see if the two samples could have come from the same distribution. Okay, so that would be the two sample KS test. So you can read more about it. But basically, we're going to test to see if the x that we generated. So remember, we created x by first doing a random uniform, and then doing an inverse CDF. Okay, so x is generated by taking random uniform and then plugging them into inverse CDF. So I take my x and I say, could this have come from this CDF, the exponential with rate equal to 1. Okay, so the KS test, you give it basically your sample of values, which is my vector x. You give it the CDF of the distribution, which will be basically, p whatever function, p gamma, p beta, p exponential. And then, if your function takes on additional parameters like a rate or a shape one or whatever parameters it is, you kind of pass those along as well. This is kind of in the dot, dot, dot. Okay, so anyway, it does the test and it gives me a p-value of 0.3886, right? So this number is bigger than 0.05. The result of the KS test produces a p-value greater than 0.05. So what that means is we have no reason to doubt that these values came from an exponential distribution, right? So we're not going to reject the null hypothesis. Again, we have to be careful in our statistical language. We can't say this proves that the data come from a exponential distribution. All we can say is that we have no evidence that it does not come from an exponential distribution, right? So that's kind of the language that we use here. All right, is this okay? Good. All right. Okay, I'll do one more for the normal distribution, and then we'll call it a day. I'll save my piecewise one for Wednesday. Okay, so here's the normal distribution. In R, when you call random normal, when you call R norm, R uses the inverse CDF method to generate your random normal values. Okay, so again, the true CDF and true inverse CDF of the normal density don't have closed form solutions, so that's a little bit of a problem. But we have the functions p norm and q norm, right? P norm is an approximation of the CDF, and q norm is an approximation of the inverse CDF. Okay, and these things are accurate to around 16 digits, which is good enough for us. So they're not the true values, but they're accurate to 16 digits, so we're happy with that. Okay, because that's all we need on the computer. So these are very good approximations. Okay, and basically, when you call R norm on the computer, R is going to generate random uniform values with R unif, and then it plugs them into Q norm to give you normal distribution values. So that's what I did here. So here I did set seed 1, and I just said give me 5 random uniform values. And I asked it to print out more digits than usual. Okay, so it generates this number 0.26550, whatever this number is. Okay, it generates this number and this number and this number and this number. Now, for whatever reason, when you call R norm, it basically takes every other value. Okay. So, okay, so we have a question. Where does the Mersenne Twister? Yeah, the Mersenne Twister comes into play in the R unif. Okay, when you call R unif, Mersenne Twister is what's used to generate these numbers here. Okay, but then so if I take this number and I plug it into Q norm, what's the number I get? I get this value. Okay, and then if I take every other value and I take this number and I plug it into Q norm, the inverse CDF function, it outputs this value. And if I take this number right here and I plug it into Q norm, okay, it's going to output this number. Okay, so these are the values that it outputs when you plug in these uniform numbers into the inverse CDF. Okay, and then you can see that. So if I go back and I reset the seed, set seed 1, and I call for some random normal values, 3 of them, okay, we get the exact same values that I got by plugging in the random uniform into the inverse CDF of the normal. Okay, so this when I plug in 0.2655, I get negative 0.626, and here I get negative 0.626. Okay, so these numbers are generated when you call R norm from R. These numbers are generated by first generating random uniform and then plugging them into basically the Q norm function. All right, so that's So that's kind of neat. All right. So anyway, that's the that's inverse CDF method. We'll continue this on Wednesday. I got more examples to do. Okay, so we'll end here. Let me give you your last quiz answer. Last quiz answer is A as an apple. A as an apple is your last quiz answer. Okay, all right, we'll see you guys Wednesday. Have a good day.